question number 3 on your homework is draw the chemical mechanism of RNase. And it also asks us, what is the evidence for involvement of the protonated and deprotonated histidines? All right, so the mechanism is going to start off like this. So we have our RNA molecule up here. All right, here's the phosphate backbone. All right, and we have 2 histidines. One of them is going to be deprotonated up here. One of them is going to be protonated. All right, now the way that the RNase mechanism is going to work is we're first of all going to deprotonate the alcohol here on carbon 2 because this is then in very close proximity to do the nucleophilic attack on the phosphate. All right, so our histidine is going to deprotonate here. The electrons that were in the oxygen-hydrogen bond will attack the phosphorus, and then we are going to protonate this leaving alcohol here, all right, using the other histidine all in one step. And then lastly, the electrons that were in the nitrogen-hydrogen bond here will just go to the nitrogen as a lone pair. All right, so that's step 1. All right, so this is all going to occur in one step. Our phosphoryl, this is another example of a phosphoryl transfer. Whenever we're doing a nucleophilic, or basically a substitution reaction kind of on a phosphate, we're going to have the nucleophile attack and our leaving group leave all in one step. All right, now we've made one of our products here. All right, the ROH, right, this bottom part here, that's part of our RNase that's been cleaved off. Well, our other product, though, is this cyclic phosphate. All right, so at this point, we need to do something with this. All right, it's important, again, to make sure you keep your histidine straight. So this bottom histidine just got deprotonated in the last step, whereas the top one got protonated. So this one is ready to serve as a base. Well, the way we can cleave a cyclic phosphate like this is by using water. So the lone pair on the nitrogen is going to deprotonate water, making it a better nucleophile. That will attack the phosphorus. And just like our last case, when we do these nucleophilic substitutions on phosphates, we're going to attack, and our leaving group is going to leave all in one step. So this alcohol, oxygen here, all right, we'll go and pick up a proton, and the lone pair, or the 2 electrons in the nitrogen-hydrogen bond here will go to live with the nitrogen on the histidine, all right, giving us our second product, which is just our the rest of our RNase with a 3' phosphate on it. Now, the second question is, what is the evidence for the involvement of the protonated and deprotonated histidines? Well, that all comes from the pH rate profile. When they measure the pH rate profile of RNase, they basically see there are 2 pKa values right around 6 approximately. One slightly above 6, the other is very, very close to 6. But they're very, very in that realm where they belong to histidine. The pH rate profile basically indicates that the maximal rate is between those 2 pKa values. So that means now that one of those groups is going to have to be protonated, whereas the other one is going to have to be deprotonated. Well, in each step of this mechanism here, we always have a protonated and deprotonated histidine acting together to carry out the chemical reaction.